Just 30 seconds and we can start. Or 1 minute, maybe, because something is waiting. Okay. Just 30 seconds and we can start. Or 1 minute, maybe, because something is waiting. Okay, Michele, when you want.
Okay. Can you hear me now?
Yes, I hear
Okay.
you.
Okay. Good morning, or whatever it is, to everybody. My name is Michele Doro. I work here at the University of Padova, and Miguel Angel asked me to talk about some facts about gamma ray astronomy. And my contribution will be in two parts. Today, it will be general on what is gamma ray astronomy. And on next Monday, there will be a specific talk about the instrument by myself too, because if I have, I hope I will show you how really we need many different kinds of instruments to be able to detect the gamma rays in their whole spectrum. So, well, let me skip the program. I can hear a lot of noise from Jigar, maybe, if you can mute him. Yeah, great. Okay, so I'm an associate professor here at the Department of Physics and Astronomy at the University of Padova. I held courses on experimental physics and physics so far. You can find my email there, and you can write me later if you want, or if you have further questions during this week, or you can interrupt me at any time. Okay, and I post here 2 links if you're curious. Now, as my background image here says, I work for especially for MAGIC telescope most of my time. These are 2 instruments that will be described next Monday, and that are taking data for many years now, almost 2 decades. But because of the advancement in this field that I hope I will show you, we are working on several new detectors. One is CTA. I hope you have heard this name. It's a very huge telescope array system. Another one is SWGO, which is a particle detector to be placed in South America at high altitudes. It's a different technique. And another one is the Trinity, the detector for ultra high energies neutrinos. Maybe some of these will be described next Monday. Okay, a disclaimer about the way I structure this talk. Okay, well, first of all, I don't know, just for fun, I got an analogy to travels. We will take a cosmic journey, and I will ask these nice figures here to explain us what are the particle interaction and what are the main player in this travel. I believe this will help to fix some information. So we will have the electron and positron. We will have the proton, mostly once the neutrino will show up. Of course, we will have the weak photons in the universe and our scary gamma ray. So many particles, and as you will see, there will be a lot to say. Okay, so because of this school is focused on dark matter, I decided to keep the structure as a seminar, not a lecture. First of all, because it's basically impossible. Cosmic ray and gamma ray really requires books to be described, and especially because the places in the universe in which you find these gamma rays are very different, and it's really hard to make a specific and a general discussion at the same time. And mostly, I think I wanted to give you an overview, and I will put some reference here in case you have to study yourself some of these concepts. Okay, so the luggage is full with information. We will start. Okay, you are a physicist, you know that gamma rays are those photons with the highest energies, and there is no clear definition of specific gamma rays, but is normally taken as basically the mass of the electron here, okay? And what we call very high energies is this most intense region in the TeV regime. A photon with one TeV, just for, I mean, the numbers are too small and too high, so it's a little difficult to remember, but anyhow, the wavelength is pretty small, is 10 to the minus 18 meters. The frequency, the corresponding frequency is 10 to the minus 26 hertz, and the energy carried by one photon is pretty large. It's 1.6 times 10 to the 7 minus 7 joule, 1.6 erg, okay? Normally, particle physicists use the n over d, the flux of photons is expressed in number of photons, differential number of photons in function of the energy. But if we want to live in an environment of sources in which we have emission, we normally quote fluxes in spectral energy distribution, which is the photon energy multiplied by the square of the energy, which corresponds to the nu f nu, so the distribution of photons in function of the frequency multiplied by the frequency. The unit is then energy per square centimeter per second. That's the custom. A little bit of nomenclature, maybe especially for next week. So there is a rough classification of the gamma rays, which is also used for cosmic rays according to the energy, just for, but it's important because it's pretty used. It's not based on particle physics itself, but mostly on the experimental techniques that are used to detect those photons, okay? So at the lowest part, we have below 30 MeV roughly, okay? Don't take those numbers that seriously. In order to detect those photons that are absorbed in the atmosphere, you have to, you can fly particle detectors in balloon. I show here a balloon. You can mount below a particle detector, which is based on the Compton effect. And then you can measure the mass, for example, of some of these particles. You don't measure the charge because you normally do not mount magnetic spectrometer in these devices. And it's also a pretty complicated experiment and costly. You have to go to the place, run this balloon, and then go and catch the instrument back. Anyhow, we will talk about those things next week. A little bit higher energies, a really important energy band is what is called a high energy. It's between 30 MeV and 30 GeV, okay? In this case, you can, the best suited technique is that of satellites. So now you can make a little bit larger instrument, you fly it on a satellite, and this is, for example, an image of the Fermi instrument, which is a calorimetric effect, but because of it's based on E plus E minus production, you can really be efficient. If you go, I will explain why this. If we go to higher energies like DHC, what happened is that the flux, I will show you, the flux over the machine here is too little. So you can detect them, but they are simply too few in the time. So you have to go to the ground in this instrument like magic. Okay, that's a picture of magic, which works until say 3100 TeV roughly. Okay. After that, again, the instrument area is too small and you have to cover wider areas and build another technique, which is called the water Cherenkov technique or similar, in which you detect directly the particle created by the gamma rays in the atmosphere. And finally, if you really want to go to the very highest energies, you have to check the fluorescence of the instrument. I will get back on Monday for this detail. Just I want to tell you that as usual, it's not possible to have instruments sensitive to more than two or three orders of magnitudes. Okay, so remember that also this naming here is normally used also for cosmic rays. Now, what is the sky? Okay, in gamma rays. Now let's start in the optical band. This is our beautiful universe, as those guys see it, and we are familiar with it. Maybe not in the towns, but if we go to astronomical site, you can see pretty well how nice and crowded is the sky. What is the gamma ray sky? Okay, so that's an image. It's a true image taken from data from the Fermi Lab detector, and that's the sky in gamma rays. Okay, you see here the wavelengths roughly. Okay, and you see this is probably the universe that would be seen by our friends, the electron and the protons. Okay. What they would see, this is again all gamma rays of different energies. They would have a very crowded region here toward the galactic plane, in which there will be many gamma ray emitters, plus several hotspots, both galactic and extragalactic, in which we expect, well, we measure gamma rays, okay? And all this blue unresolved region here is also gamma rays from the diffuse sky, okay? That can really fill the universe. There is a fun fact, okay, about the gamma rays, is that, well, if they are not that much energetic, like in the GeV band, in the high energy band, that's what you would see, okay, from the sky. But what if they are really, really powerful gamma rays, okay? Well, that would be the sky in very high energy, extremely high energy gamma rays, okay? Why black? Why black? Because at a certain point, the cross section between high energy gamma rays and low energy photons, and you have everywhere photons from the cosmic microwave background, becomes measurable, and the cross section, I was saying, for pay production become sizable. Okay, so at a certain point, you cannot see, so to say, as far away as you would like to see the universe. Okay, so not only you need different instrument, but also according to the classification of gamma rays and the energy, you cannot probe the same parts of the universe. We will have a little more time to discuss about it. Okay, the only traveler which wanna be alone, and you'll never catch him, and can travel wherever he wants, is the neutrino. Okay, so if you see here this plot that I took from Halpern, there is the distance here, and there is the energy in general of the particle. Going toward higher energy at a certain point, this is the profile of gamma rays, in which if you go higher in energy, you really have to, you can sample only regions that are very close to you, okay? At the very highest energy, gamma rays cannot come from outside our galaxies, for example, okay? Well, there is resurrection here due to some mechanisms, but anyhow, we are not able to sample gamma rays. We never saw gamma rays in this part here. Okay, so gamma rays, you can probe the whole universe, say, until 10 to the 12 TeV, say, or GeV are here. Okay, but then when you go to the TeV, like magic, the universe is not transparent anymore. Okay, and neutrino, of course, it's a perfect messenger, but it really doesn't want to be catched that easily. Okay, what is the importance? in few words of gammas. We know it for dark matter, but imagine, I mean, it's a traveler that, okay, maybe at the highest energy not, but it travels back to the point of origin, okay? So it's a straight traveler. It doesn't care about the galactic magnetic field, while protons or any other charged particle, it's scattered around. So you are in the Earth, you want to see what's happening out there, you need a neutral messenger, okay? The neutrino is okay, but as you see from the image, you do not catch it that easily. Photon, you can catch it either from the satellite, as I was showing you before, or from the ground, as you see it here. Okay, so that's the main importance of gamma rays, because really we have this knowledge of the place of origin. Okay, the risk is this absorption that I was mentioning before by the highest energy with the lowest energy photons. Okay, that's why travel stories from gamma rays are that interesting, because they can really tell us where they're from. Okay, we will see something about the protons. There is a lot of interesting information from cosmic rays, but not exactly on the site of origin. Okay, here we are really probing with our detectors particle physics happening very, very far away from us. Okay. I don't see the time, but anyhow, the story of cosmic rays cannot be said if we don't talk about cosmic rays. Sorry, of gamma rays cannot be said if we do not talk about cosmic rays. They're really linked together, and you cannot understand one without the other that easily. Okay, one can think that the gamma ray is the traveler, and that in some cases these electrons and protons are the engine that fuels up. Okay, well, the engine, those that really push up the photons to this travel. So we have to tell something about the cosmic ray, and it's a beautiful story, really beautiful and very, very interesting. It started with more than a century ago with Victor Hess, this guy here, that was together with other people at those time was studying the discharge of an electroscope. You remember this from a study, and you know that if you charge these, the leaves, they separate, but even in vacuum, they were observing that these leaves were collapsing at a certain point. So they understood that there was some radiation that was crossing the glass and entering there, so depositing charge. Well, what they thought is that the radiation came from radioactivity in the ground. Okay, so what you do, you mount your instrument on a balloon here. Okay, and that's probably it's very young PhD students, or I don't know, I'm not sure about it. But anyhow, what they saw, this is not only the Hess measurement, this is also other data of those time, but you see those years, that the number of ions, the number of charged particle measured, they were actually increasing with the height. Okay, they didn't expect that. They were looking for the other effect, so that the discharge was so to say, the vanishing at higher altitudes, because if it came from the ground, but it was coming from outside. Okay, and that's why they understood it was cosmic particles. It must have been fantastic. But it's even more amazing, the cosmic ray spectrum in this version that I show it. This is the cosmic ray spectrum as we know it, from the lowest energies here to the highest energy, and that's the flux in number of particles per square meter per steradian per second. Okay, it's really amazing. Look, it's 19. It's 10, not 19 orders of magnitude in energy. Okay, you have from GeV here to 10 to the 21 here, okay? But what is even more interesting is the orders of magnitude in flux, okay? Look, here you have one particle, and here more, but here you have one particle per square meter per second. In this region that is called me, you have one particle per square meter per year. And over there, you have one particle per kilometer square per year, or even per century, in case of the highest particle. The highest particle is about 10 to the 21 electron volt. Okay, then here you understand that it's not possible to have one detector measuring all these particles. And also what you see, and what is amazing is the regularity of this spectrum. From, you see, in this reading here, the power law is about e to the minus 2.7. There are some changes because it oscillates a little bit above the knee to -3, and then to minus 2.7, and then a little bit more, okay? But anyhow, it's extremely irregular, okay? That's really amazing, at least to me. And yes, that's mostly the spectrum of the energies of protons, okay? Not alone, but the proton is the best traveler for very long distances. Now, if we look to that spectrum in more detail, we have this beautiful collection made by Carmelo Evoli. You can see it here, the link. And you see that it's actually more complicated than that. So that spectrum is this one here. It's composed of a few more subspectra. And you see that the proton spectrum is not, the particles say, is not alone. It's very crowded because there are other travelers like proton, antiproton here. You have electron and positrons. You have positrons separately, if you can measure it. And you have some diffuse gamma here, diffuse gamma from the interstellar fields. You have neutrinos and so on, okay? And what you see here is that really you need a huge number of instruments to be able to grasp something of it. And sometimes those instruments, like here, they do not even agree. It's pretty complicated, especially here, when you have very, very rare particle, less than 1 per kilometer square per year. It's a pretty tough measurement. And also you start to see some more spectral features on this cosmic ray, on this regular cosmic ray. I will come back to that. There is not only protons, there are helium and other heavier nuclei, and this is their spectrum multiplied by some factors for observability, and you see how alike they are, okay? So the mechanism for acceleration must be the same. You see how iron is really getting to the highest energies. This will be, because it's a stable atoms, and you see how many instruments are needed to get to those results. Okay, what about the features? You see that there is, it's a strange leg. There are one knee, there is another, there is an ankle, but there is also another heavy knee, okay? A heavy knee, it's due to iron, because as we will see, iron will be, can be accelerated to higher energies, okay? So that's one feature here. If you multiply by a certain factor, you will see it better. There is another feature that is the high energy end, again, in which you have detectors making sometimes not very, so to say, similar measurement, compatible measurement. You need a lot of them. And this happens, this was known for some time, when you are really at the highest energies, you cannot increase more the energy, because both the protons and the atoms, again, they interact with these low energy photons from the cosmic ray, cosmic microwave background, and make you pions and other particles. So that's called the Greisen-Zasmin-Kazmin cutoff. Okay?
Excuse me?
Yeah.
I have a question. the flux that you measure or that you have been showing, it doesn't depend on where you are looking at. Because,
no, I will get back to that. But anyhow, you measure from the ground, and as you remember, the discharge particles are scattered. So actually, you don't see into one direction, okay? You basically get photons from any direction, except for the very highest energies, okay?
but
So
I mean,
yeah,
the measurement of cosmic rays.
cosmic rays are charged.
Yes, so my intuition says that if you look at the center of the galaxy, in principle, you will measure a bigger flux than if you look at different.
No, it's not like that because of the effect of the magnetic field.
Ouais, je donne
Your
un cours à
intuition.
de midi et quart à 2 heures. Donc, je vais essayer de manger avant puis d'aller au bureau pour que ça soit une meilleure
I can
connexion.
hear some noise. Can you mute your microphone if you're not making questions?
Yes, please. Remember to unmute all the microphone, please. Okay.
You can do it
get it.
probably as a host. You can mute everybody.
I just did. No problem.
Okay, thank you. And so, yeah, your intuition is right, but only for the very highest rigidity particle. I will get back to that. And it's not from the galactic center.
Okay.
Okay, another anomaly, another feature is, for example, what you see in the anti-positron, in which you may expect a certain particle distribution depending on the energy and the weight and the velocity. And this is measured by the instrument on board the satellites, okay, like AMS. This is the positron. But recently it was found, for example, that you have a very peculiar shape, like you have a flattening and then another bump here. How do you call it? It's positron, but this must come from another population of positrons. And this was long debated as a dark matter contribution, but can be, it's most probably made from other close by particles, okay? So here your intuition works, okay? Positrons from local vicinities can give you some hints, but you don't see any direction, okay? So this is from any direction in the sky. So the protons, they do not tell you where they're from. This is what we were discussing because of this. And it's not only the extragalactic, but also the galactic one. The only association that was found happened very recently. A few years ago by Pierre Auger collaboration, we will talk about that, in which for very high rigidity, high energy protons, okay, there is a positive association to extragalactic active galactic nuclei, okay? It's not strong, it's not extremely statistical sensitive, but they are crowded over AGNs, okay? But it's the only information in which we can see this anisotropy in the sky. Okay, where they're from, we can say that below the knee, they are, so to say, young traveler, and they must come from the galaxy, and we will get back to that. In order to have cosmic rays above the knee, you need to have old travelers that comes from outside. We will see that it takes more time to measure, to accelerate a particle to the extragalactic, to that energies. Okay, and also the bottom part of the plot that we were showing, you see that this is again the energy and the flux, and you see the diffuse flux of photons, of neutrinos, and of cosmic rays. They share the same energy flux. Okay, this is pretty interesting because it's a strong hint of connection one another, as it is expected from particle physics. Okay, so if you want to study neutrinos, you have to study gamma rays, and if you want to study gamma rays, you have to study cosmic rays. It's pretty they're pretty linked together. So let's make a little pause. I was saying that I will not make too many equations here. I recommend here few books. They are pretty extended, but you can find them and check for some chapters there. These are the best one that I know of, but there are surely many. There is also a very short, but as usual, very interesting, this particle data group review is biannual, and the chapter about cosmic ray is pretty interesting. You will find many of the plots that I show, and it's a few pages, really concentrated and clear information. Okay, if you're with children, you can also take some fun books. But again, it's important because the amazingness of the spectrum, I think it started to touch many people, okay? And it's not recently. I want to show here the picture of a movie from 1957 from Disney, okay? Really back many years ago. The title is The Strange Case of the Cosmic Rays, and you can find it here in YouTube. And the opening words are, "Wanna see an out of this world true detective story," because they were really investigating in this movie the origin of the cosmic ray. You have two human characters, they're scientists, but they couldn't resolve the riddle, so they have to contact the Academy of Detection, Arts and Sciences. And for some reason, the three persons to whom they asked were Charles Dickens, Edgar Allan Poe, and Dostoevsky. Okay, these three guys, they were trying to find the answer to this truly out of this world detective story. Yeah, it's old times, but it's available now. Okay, so how do you fuel up for a long intergalactic travel? Okay. So if you want to accelerate a charged particle, you know that you can use electric field, but in the space, you cannot really have a plug to keep them alive, okay? So if you have charges around, they will dump easily the electric field, which is then neutralized, except in some very peculiar places in the sky. It only works if you have few charges around, but then if you have few charges around, you don't have a strong electric field, except in some cases. Most of the acceleration comes from magnetic field. And again, if they're permanent, you just make particle rotate. You need to have variable magnetic fields to have particle acceleration. Okay. It's not only the engine acceleration in the space. You need to have very nice places like this supernova remnants. Is not a jellyfish. You need to have, as written here, a geometry of the object. Okay, you should maintain the acceleration. Is not instantaneous. So within the geometry of the object, you need to have enough power in the source to accelerate the particle, and density to have a certain emissivity. And then you can lose the energy you gain by radiation and interaction losses, okay? So you have to check also what's around, because you can lose what you have gained. So what is the basic idea? If you don't know anything about this, but you know that there are stars that explode in the sky, you may think that there is just conversion of kinetic energy, then the energy of the cosmic ray is just kinetic energy by the explosion. This is the basic idea of Zwicky and Bade on 1933, okay? But they realized that is not enough to get energies to the energy that we discussed before, okay? So the genius is often Fermi in the group in those years. And this is an actual picture of his notebook with a date, number of pages, and theory of cosmic rays. And it's just one page because it ends here with this very fast calculation in which he thought about a mechanism to accelerate the particle. I believe he got the idea while studying the atomic bomb that the stars that explode may be considered like atomic bombs. So the idea is that you have an expanding shell of material, but in the space it's embedded with charged particle and then magnetic fields, okay, very turbulent ones. And then that the charged particles, the free particles that are there, they can get accelerated by stochastic acceleration, okay, by bumping into those shells of expanding material. That's the basic idea. And it catches the truth, okay? So there are two mechanisms, and this is the historical one that was published at the end of that famous page, and it's called second-order Fermi acceleration. Basically, it's not that you find it in all textbook. The computation is again what I was saying. You have a charged particle, you have an encounter with some blobs, clouds of material, and you get a deflection. But you get, if you count, you get an average positive acceleration of the particle by the cloud. Okay. If you compute the probability of encounter and this little gain of energy, you have that each time you have your energy get augmented by a certain fraction, which is proportional to the square of the velocity of the cloud, okay? The velocity divided by c, okay? So it's positive. You can slowly, by successive encounters, accelerate this particle. But the problem of this method is that it's low, okay? If you take the cloud velocity, is not so high. And so at the end, you can accelerate, but it will take you too long time. At the end, you will not be efficient. A few years later, Fermi himself, he said, well, yeah, but is this cloud of expanding material that random? Okay. And he realized that it's actually not, okay? He realized that when you have an expanding shell like this, you have the formation of shock fronts, okay? This blue part here is a shock that is expanding. A shock is a region of the place in which the density, the shock front, is very different from what is upstream. So again, the mechanism is simple. You have a particle, charged particle from the ambient medium here, the upstream, that get beaten up by the shock front, which acts like a piston. It goes to the downstream, but then there is a good probability that is reflected back from the region downstream to the shock front. Okay, and in a certain sense, this mechanism goes along by reflection. So sometimes it's called magnetic mirror reflection. Okay. And believe it or not, if you compute the probability, okay, you get this particle trapped, and as long as the shock exists, these particles are slowly accelerated. Okay, you count the probability, you get now that the increase of energy by this mechanism is linear with respect to the velocity of the shock. Okay, so if you wait for a few hundreds or thousands of years, you have high energy cosmic rays. Not only you compute the particle spectrum, you compute the energy gain, and you can, from those, compute the spectrum of cosmic rays and photons, and you get this photon spectrum with an index of -2.5, which is not that different from the -2.7 that I was showing before in the cosmic ray spectrum. So Fermi got it, the main idea, and this mechanism is the main one is called diffusive shock acceleration. Okay, so what you need is embedded irregular magnetic field to have this gain. Okay, so do we have a magnetic field around in the universe? Yes, we have many of them, and there is this beautiful plot that is called Hiller's plot. It's this guy that died recently. You have the size of the emitter and the strength of the magnetic field. So that's what you get in the Earth, in the LHC. You see that it's not that much compared to what you had, for example, in neutron stars, in which the object is very compact, but the magnetic field is pretty large. And on the other side, I will not go there to explain all this. We have instead the active galactic nuclei, in which the size of the region is really now big. Okay, so the magnetic field can accelerate particles for very large distances. Okay, and these lines here, they tell you the maximum energy that you can have for including losses. Okay, so this is like a simplification line. If you include the losses that you have, you can accelerate particle up to this part here. Okay, so the Hillas relation, Hillas criterion, is the maximum energy that you can give to your cosmic rays depends on the charge, depends on the magnetic field, and depends on the radius in which you can have this acceleration. Okay. So we saw the pulse, the supernova remnants. I will get back to that. But the biggest engine on the other side is these active galactic nuclei. But again, you have, okay, we will get back to that. You have a central engine, you have ultra-relativistic jets here, in which the magnetic field is really strongly embedded. And you have the time here, you have cosmic time, millions of years to accelerate your particle. Here, you have just thousands of years, but you can get pretty high energies too, okay? So it takes time. What's interesting about this black hole, it's another fun fact, just to relax a little bit. This is a computation by Gabriele Ghisellini. I like it very much. So he was computing in a school the conversion efficiency that you can have when you try to convert matter into energy. So he was computing the efficiency of conversion, say, of energy from a water central, 10 to the minus 14, from a windmill, 10 to the minus 15. Okay, you want to convert the energy in the cell from the amount of sugar that you have into energy. It's an efficiency of 10 to the minus 10 from the matter of sugar. Well, for the nuclear fission and fusion, you can reach now efficiencies of 10 to the minus 4, pretty high compared to normal mechanisms. This is the central black hole. You convert the gravitational energy to the mass, okay, and you can get efficiencies to up to 0.1 or 0.3, okay. These are rough numbers. There will be, of course, a lot more to say, but you see how a black hole, especially of large dimension, can be a very efficient converter of gravitational energy of matter unfolding into energy. And that's why we have this powerful jet, here, in which you can sustain an acceleration for millions of years. There are other means of acceleration. I will have to move a little bit faster here. This is the pulsar, okay? So a compact object that forms, I will get back to that, at the center of an exploding star. Here, the mechanism, the geometry is very peculiar because you have a very small object, 20 kilometers in mass, rotating at very fast millisecond frequencies. You have a magnetic field that is embedded into a light cylinder. There is a light cylinder because if you count if this object is rotating here, the velocity of the magnetic field would be larger than the speed of light of the electromagnetic field, and so there is a light cylinder. It's a pretty tough place. Here you can have one-shot acceleration. There are very strong 10 to the 12 Gauss and very strong electric field. And here you can, in one shot, if you can do it, accelerate energies. It doesn't matter about the formulas here. I just want to make you the grasp the acceleration. Okay, and finally, there is another mean, but it's less relevant most of the times, is that within this huge ejecta, you can have strong magnetic field, and there is the possibility of having reconnection, so that the field lines they change the direction, and in that moment you have like one shot, very intense magnetic field, not that many charged particles around. You have a boost in the flux. Okay, I don't have the video, but you can find nice videos of this image here. Okay, but again, mostly is diffuse. Let's keep the first mechanism, diffuse acceleration, as the most important one. So up to now we were talking about cosmic rays, and now we move to understand how we generate gamma rays of very high energy or high energy out of those cosmic rays. Okay. Well, what is the idea? And it's pretty intuitive. If you have accelerated particles, they will have to cross some fields. Okay, they have to cross a custom. What is the custom? It can be matter. Okay. And according to the particle that you have there, you can have pion decays, you can have electron Bremsstrahlung mainly, you can have positron annihilation, and if they can encounter radiation field, in which you can have pair production. Okay, you can have inverse Compton, photon production, so P gamma. And you can interact with magnetic field and make synchrotron radiation, okay? Lose energy by synchrotron radiation. Now, all these processes, you know, from your studies, and you can imagine here, we will see, but we already see that we have from very compact object to extragalactic object, the size is pretty different. It depends really on what you have in your region. If it's a region matter dominated, you can expect some of these guys. If it's a region radiation dominated, you can expect most of this interaction. And if you have very strong magnetic fields, other interaction. So there is no single theory of everything, and you have to become an expert of that peculiar class of object to understand what are the most important interaction that are at play. So for this region, I have decided to structure the lecture in some way, and this is the usual way in which is done. So one way of doing this, let me get back, would be to discuss every single of these channels, as is done in some books, every single, and try to discuss the spectrum of primary particle, the spectrum of secondary gamma rays coming out from those particles. You can estimate the maximum energy, and it's pretty interesting, okay? But you lose a little bit the idea, the main idea behind. And again, this you can find in all of the textbook. Because at the end, what matters more is few of those processes. So this picture I took from Fabrizio Tavecchio. And what is interesting it's a good classification is of this gamma ray production mechanism in leptonic and hadronic, okay? So leptonic at the end of the day is mostly electrons and sometimes muons, okay? In some occasions. Electrons, you have all the electron processes here, the electron synchrotron, we will discuss a little bit, and the inverse Compton scattering. But then if you have a region, for example, in which you have strong radiation fields, also the photon pair production will happen. If you have strong presence of photons, you can annihilate very well the antiprotons, the positrons, okay? Or the other channel is the hadronic one, okay? Surely you have proton synchrotron, but you know, we'll see, but you know that this is not that efficient in general, unless you have a very strong B. So again, this depends on where, well, it's written here, where it requires high B. And then when you have a cosmic ray, what will it do? Well, in regions with high photon densities, you can have photo production. So you have particles, and then you have emission of gamma rays indirectly from here. what is more common is the interaction of cosmic rays with other dense region, okay? And then you have neutral pions, and then you have gamma rays from neutral pion decay. So pion decay here. Okay, so you can imagine any place in the universe you go, you will have all of these, but in different strength. So it's normally classified, the gamma ray astronomy, as gamma rays of leptonic origin or of hadronic origins. Why? Because of what I said, and because electrons are easily found, okay, in all astrophysical environment, and are pretty easy to accelerate, okay, because of their mass, and because of their mass mainly. For the same reason, they can also cool rapidly, okay, or get absorbed. So you find them here and there in the universe, but you cannot expect to have them traveling very far away from the location of the source, okay? Magnetic fields are everywhere. This we saw already with the Hillas plot. Okay, so the main mechanism to have photons from electrons is the synchrotron radiation. Okay, I don't need to go to the formulas to know that the efficiency of these depends on the mass of the particle, and that's why this works very well with electrons and not with protons. Okay, so once you have B of the order of the Gauss, you can have MEV or GeV, well, KeV, mostly synchrotron radiation, okay? But what this would not be enough to get these mechanisms does not allow you to have tera electron volt or even higher energies. It stops at a certain point. In order to reach the highest energies, there is another mechanism which is called inverse Compton. Okay. Now you know what is the Compton, the direct Compton scattering. You have a photon of energy E transfer energy to a low energy electron. Okay, and at the end of the day, the scattered photon has a lower energy, E prime, smaller than the initial energy. Okay, it's a upscattering of electrons. But in space, you have the opposite situation in which you have normally a lot of high energy electrons and a lot of low energy photons from EV photons from even thermal mechanisms. Okay, so here is where the inverse Compton is probable. So it's a transfer of energy from the electron to the low energy photons. So the electron has high energy. This is a low energy photon. This is the electron after, and that's a high energy photon. And here, the exiting photons can now reach the TV. Okay, it's pretty easy to transfer that energy. The electron is ultra relativistic and transfer easily a huge amount of energy. Okay. And not only it works, but if you remember from previous slides, what you can have is that you have electrons. If you have a magnetic field in this game, you can generate lower energy photons, these guys here, directly from synchrotron radiation. Okay, so there is a way in which basically the photon that you upscatter are the synchrotron photon emitted by the electron itself. That's why it's called self-synchrotron Compton, okay? Because it combines the two. And believe it or not, this is what we saw basically everywhere in the sky, okay? So that's a plot that is the logarithm of, well, it's frequency or energy, and that's the flux that I was saying before. And these are, this is a simulated one, but it's very typical, I will show you, of astrophysical targets. So you have this red distribution of gamma rays that have the shape of the synchrotron radiation, okay? There is a population below here of electrons with a certain shape, and this is the synchrotron radiation. It peaks in the UV, a little bit higher energy, can be up to X-rays, okay? Those same photons here are upscattered by inverse Compton into this distribution of TeV and photons here, okay? So it's basically the same cosmic ray seen twice. This is called the synchrotron bump. This is called the inverse Compton bump. Okay, so they're really traveling in family. And that's why we will see, we don't see orphan flare. Well, this is maybe too premature to say. We'll get back to that. Okay, so can you imagine if you can shape and observe all the spectrum in all the wavelengths from radio to gamma rays in photons, you are able to tell what is the population of electrons at the source. This you cannot do with cosmic ray physics. You have to do with gamma ray physics, because with gamma ray physics, you probe exactly what's happening at that source. Okay, so that's called synchrotron self-Compton. Because I was fast, I want to tell you that you can learn yourself and teach yourself some things. There are that spectrum that I was showing, this one, okay, was taken and produced with a code called JetSet. There is JetSet, there is AGN Pi, you have all the links here, there is NIMA. All these codes, they are focused more on the jet, but as you see, what they study is diffuse acceleration. So they are very well written and with many tutorials, and you can study, for example, the connection between the different shape produced by the same particle population into external Compton, so Compton with external fields, or synchrotron self-Compton. You see the difference. You can connect the synchrotron peak with the inverse Compton peak and make some studies there. You can even simulate a full spectrum, okay, and separating the contribution of this interaction of the cosmic rays with the ambient background. And you can basically learn, okay, how from a parent particle you get to a gamma ray spectrum, okay? If you're curious, really go there and ask me in case you need support, because we know we work with these people, okay? It's not so clear, it's not so easy, because every object in the sky is in a certain sense unique. For example, for the AGNs, there are different classes of objects. Here, I don't want to go into the details, and the spectrum that you see the position of, for example, the synchrotron peak changes by 6 or more, or 5 orders of magnitude, okay? As well as the inverse Compton peak. So, and this is the blue part here is the galaxy that sometimes is visible, sometimes is not visible. So there are very, very strong differences. But what we are trying to do is to sample the spectra to get a grasp on what are the cosmic rays below. Well, let me skip this part here, okay? Now, for the hadronic gamma ray acceleration model, here what you must have an accelerated proton, okay, that makes some interaction with the matter. Now, we saw how we can accelerate protons for the same mechanism that Fermi was describing. The problem here is that it takes more time because of their mass, but they can diffuse more. So you can find them farther from where they were firstly produced, okay? Now, the main process here for the hadron is the pion decay, so interaction of protons with matter. In case you have very strong radiation fields, you can also photoproduce. So you have proton gamma giving you pions and then photons. Okay, the pion decay, the basic feature is this dependence of it's a pretty constant cross section, about 30 millibarn. And there is this relation here that we will use a little bit further, in which tells you that you can have hadrons as pions or hadrons as nuclei, and the nuclei the nuclei interaction can get to a little bit higher energies because of this dependence with the atomic number. Okay, so you have proton and proton, and then you have your pi zero, and then you have the decay of your pi zero. Most of the photons, high energy photons, comes from the energy of the pi zero in the universe, okay, and are representative of this population of protons. The spectrum of pion decay photons is depicted here. There are no units, so it's just a figure. This is energy and this is flux. You see that in general, while the inverse Compton spectrum has this shape, the pion decay for kinematic reason has this different shape. So there is both a harder, well, a very strong cutoff here, but especially a harder cutoff at the lowest energies. So if you're able to observe a target in the sky and you can see this shape, this is really strong signature that you have protons at the source, okay? Charged particle and not electrons, as you would have with this line. There are other ways. We were talking about mechanism of production of gamma rays. There are other ways, a little bit lower energies. You can have nuclear de-excitations. You can have lines. Okay, I'm not an expert of these lines, but I'm just putting some numbers here. And of course, what you have is the topic of this school. You can have gamma rays from dark matter too. Okay. But as you will see, and that's what I want to give you as message, that you will have a lot of background, okay? Depending on what you're looking for, dark matter, you have a lot of background in gamma rays, this you probably know, but also now you should be able to understand that you need to know the cosmic ray particles too, to get an understanding of your limits, in case, especially in case there will be a detection. Okay, now in the final part of these slides, I want to tell you something about the astronomy, okay? I don't know if you have questions and you want to ask me, I can stop here for a few seconds. Okay, we can leave it to the ends or afterwards. I know that I'm giving you a lot of qualitative information, but I want to give some messages and I have to run a little bit. So we were saying that we saw now this connection between gamma rays and cosmic rays. And we saw through the Hillas plot that we have magnetic fields everywhere. But at the end of the day, this breaks down into really several classes of objects in the sky that emits gamma rays. You have extragalactic objects, okay? They're not the same. Radio galaxy, blazar, FSRQs, galaxy cluster, gamma ray burst. We will discuss them briefly. You have targets in the galaxies which can be different. Supernova remnants, pulsar with nebula, globular cluster, binaries, novae, pulsars, microquasars. Okay, and then you have all these uncertainties in the cosmic ray fields, like the jet, the shots, the intergalactic magnetic field, the EBL, these low energy photons, plasma, and so on and so forth. Okay. How do you make a single theory out of it? It's really, as we started to discuss, it's really very complicated. It's almost impossible to have a single view. It's true that the synchrotron Compton mechanism, the pion decay, they are everywhere, but the amount, the specificness of the spectrum that you have for these sources is pretty different. And you have to know many details of each sources. That's why I underline the word astronomy, okay? Because at the end of the day, if you want to do astrophysics, you need to know what's happening throughout the whole spectrum of radiation from a specific source. And that's what we call astronomy. You need to observe targets for long times, throughout the years. You're not doing an experiment, you have to repeat it. You have to understand if the target is one of a class or not, okay? So there is a lot of knowledge that must be shared with astronomers, not only with particle physicists. Okay, that's why this field is exploding now with knowledge and information. So if you want to start working on gamma ray astronomy, even for example for your dark matter targets that you like most, you have to know where you are looking at, okay, in the universe. Where are you? Okay, this is a nice picture from Bertola, which tells you, okay, if you go from the Earth to back in time or further in distance, you see that you have different constituents. And we saw that it depends a lot if you're looking at galaxy clusters or galactic objects or farther away, in order to understand your gamma ray sky and to understand the mechanisms that are behind there, okay? So are you looking at something in the extragalactic space? Then you have to know the magnetic field there. Are you around the compact object? You have to know all the details of the acceleration mechanism there. Are you close to a supermassive black hole or to a binary system? Okay, I think you got what I want to say. Not only this, okay, so this is where, and this is also the distance point that I was telling you before. We can see gamma rays from the sun very close, but we can see gamma rays from nearby stars, the Milky Way, satellite galaxies just outside our galaxies. And we can follow this hitchhiker guide to the galaxy to have a grasp. But there, nothing is written yet. We would need an extragalactic guide. The farthest TV emitter is 1 gigaparsec, okay? 1 gigaparsec when the universe was half the age it has now, okay? We don't know everything, of course, okay? So not everything about the gamma rays at those early times is known. So there are many questions still to be answered. Also, let me show you this video that we made with, this is me, my colleague, and these are high school students. We put out a GIF, animated GIF of the targets. You see the time by here, 97. We knew of one source, the Crab Nebula, and then only few TeV targets were under observation, okay? So our knowledge of the high energy gamma rays is very recent, okay? Is not absolutely completed. What we are doing now is to have more and more astronomical data about those sources, okay? But we do not have an unbiased knowledge. We are just looking at, so to say, single experiment. We are trying to repeat the experiment as many times as we can. But our sky is not populated. I will get back to this when we'll discuss the instrument. But as you see, it's a very, very recent field, okay? You have a different class of emitter now. If you want to study, we want to see the basic peculiarity of these studies, of these targets. And as you see, they are sparse in the sky, except for the galactic center, where we have many unidentified objects, but we expect to have many supernovae, many pulsar wind nebulae in this galactic center region here, okay? So this is at the very high energy of the universe. Now, what are the most important GeV and TeV emitters, okay, in the galaxies? These are basically connected to the end life of a star, okay? The end life of a star, you know, maybe from some astronomy course that when a certain stars of certain masses, they get to the end, they do not burn they do not have hydrogen anymore. there is the gravitational pressure is not counterbalanced. And what you have a sudden compression and then a sudden expansion of the targets. And you have the shell of a material we encountered already expanding and creating the shock that accelerates the particle. You have supernova, you have pulsar with nebula a little bit inside, and you have this pulsar that is the remnant that is at the center here, that is a neutron star that is rotating. We saw already that these are places in which you can have particle acceleration. Now, for dark matter searches, maybe you're not really pointing at a supernovae, okay? But suppose that you want to take the limits from a dwarf satellite galaxies or a globular cluster of stars. You have to know how many supernovae you expect. You should be able to compute how many interloper stars you have when you compute the J factor. So it's pretty important to know what are the expectations for GeV gamma rays from these guys here. Okay, this is connected to the death of stars, and there are also emitters when the star is actually too alive. When you have a pulsar and it's very close to another massive star, like a B star, what happens is that you have, they can compose, and it's very frequent, a binary system in which, depending on the system itself, there is an aphelion and perihelion distance and the longest distance. In some of these, when they are close one another, you can actually see the signature in gamma rays from the accretion, okay, of matter from the star to the pulsar, okay. This can be, there can be in this way a creation of, again, shocks because of these winds of particles. And we know that when we have winds, we have this diffusive acceleration mechanism. In some cases, you can even have like the turning on of relativistic jets. This is not an AGN, okay? This is a pulsar. This is a smaller object. This is a star. And the accretion is so important that you can have magnetic field here that are able to sustain a relativistic jet. This is called a microquasar object. So about the stellar end products, what you need to know probably is that you have two classes of object. The type 1a we heard yesterday from Jesus. The importance of those targets is when the accretion on the white dwarf exceed a certain fixed value, okay, of critical mass, and so you have you have another acceleration, another explosion, which has a very stable brightness level. And then you have the standard core collapse mechanism that I was telling you before. Lack of hydrogen, contraction, rebound, and explosion. Neutron stars, you may remember from the HeLAS plot, you have magnetic field of the order of 10 to the 12 Gauss, okay? So the maximum energy that you can have by the HeLAS formula, it's on the TV. And they rotate of the order of 1 millisecond. These two numbers can be calculated by conservation of angular momentum and magnetic field from the dimension of the star to those of the neutron star. The ejecta that are here, they can travel to 10,000 kilometers per second and have a magnetic field of the order of the milligauss. But then they can stay there for thousands of years, okay? So in all cases, what you have here is winds of particles that allows you to have acceleration and then to have gamma rays. Surely leptonic, because they are galactic objects, so electrons are easy to produce, but also hadronic mechanism can be at place. I want to show you here how complicated it is, the scenario, if you look at it in the details, okay? So this is a picture from Gwen Giacinti. It's pretty complicated, but pretty nice. So take the first 10 kilo years after the explosion of a star. Okay, you have the pulsar at the center. The pulsar is these messy things that is rotating and it's able to accelerate particle around and create a shock that is called pulsar wind nebulae. So a wind powered by the pulsar. Outside, you have the ejecta, which is properly called the supernova remnant, that is also an expanded shell. You have the front shock, you have the reverse shock here, okay? And this is another region in which you have particle acceleration. Now, it's likely, no, that the pulsar has some kick velocity here, for example, in this direction. And so after some times, 10 to 100 kilohertz, well, the winds are a little bit more dispersed. But then this particle acceleration is less ordinary, so to say, less ordered, up to a point in which the pulsar itself can be totally disconnected from its supernova remnant because of its velocity. And you can have this, or this in your data, okay? These ones, it's called properly the pulsar wind nebula. This one is called the supernova remnants, and you can have the composite winds like in this phase here. If you don't believe this is a beautiful picture of what was the picture here. You see here the supernova remnants. This is not TV energies, lower energies, but anyhow. And this is the pulsar that has left the supernova remnant, and this is the tail of acceleration of particles that is emitting, okay? So you may understand that there is not all these objects are alike. So each one has its own story to tell in a certain sense, if you want to look at the details of that. So the acceleration is in these guys, in the winds, is what we were discussing before. The kinetic energy of the winds create shocks. The shocks embed turbulent magnetic field, which is able to accelerate cosmic rays by the Fermi mechanisms. And then you have gamma rays, mostly by inverse Compton, either with external photon field or with synchrotron photon field. Or you can have pion decays. This is, for example, a spectrum of these guys here, this guy here, the Crab Nebula. And you see again that it goes from 10 to the minus 5 EV, so X or radio, to 10 to the 15. This is the synchrotron bump, and this is the inverse Compton bump. Okay. Here you look at this, and you can trace the particles that were able to generate those signatures. Okay. The maximum energy depends on the charge, the mass of the particle. Okay, this is interesting, and I will get back to that. So the maximum energy from a pulsar that you can have, it's roughly from a supernova, sorry, 300 TeV multiplied by Z. This is an example of these guys, okay, of the supernova remnant from Hess. It's a friend experiment of MAGIC. This is the data. And this is the model if you see leptonic, if you assume a leptonic acceleration mechanism or hadronic one, okay? The morphology is a little bit different because protons have different diffusions, but you can see that you can do a lot of particle physics at the source. The morphology is different, and as we said before, the spectral signatures is different. So by observing this, you can say if there was a lepton or a hadron there, okay? Pretty nice. And by this formula that I displayed there, we learned that those cosmic rays below the knee, okay, below 300 TeV or so, can come from the galaxies, okay? These guys here, the young one, can come from supernovae, mostly, okay? There is sufficient budget if you count the number of supernovae that explodes. You can have also the fluxes, you have the energy. So all the protons here can be explained by acceleration in supernovae, okay? And also the dependence of Z can also explain the heavy knee, the iron knee, no? The iron can be accelerated more than the proton, so you can have this second bump here due to galactic iron nuclei accelerated a little bit more. Okay, we have the jets I was saying before, microquasar. Again, we have infall of material that can create ultra-relativistic jets in the galaxy, so much smaller scale than the extragalactic sky, but still pretty intense energy and high energies. And what is interesting here, at least to me, is that here, these beautiful jets that you see in the galaxies, they are not always there, okay? You can see them for 1 or 2 days, depending on the geometry of the system, and then they can leave you, okay? So you have your gamma ray sky from the galaxy is pretty variable. So you can turn the jets on and off on a scale of days. You have the pulsar, you also have pulsed emission, okay? So this is not energy, this is phase now, because the pulsar is rotating. I don't have a video. You can have pulsed gamma rays here, this is milliseconds, more or less. So you can have like a flash in the sky. I don't have time to go into the details here. And again, by knowing the particle, the spectral shape, you know what is the acceleration mechanism there of the particles. And instead, if we move to the extragalactic sky, we are now moving outside our galaxies. The main player is this active galactic nuclei. Okay, we will spend some time on those. This is most due to them, the GeV TME emission, but also to places in which you have a lot of activity, like starburst galaxies. Okay, now models of active galactic nuclei, and I have to go toward the end. I'm almost there. You have a supermassive black hole, to make one. Okay, here it must be like a little bit larger than the one we have in our galaxy, so 10 to the 6, 10 to the 10 solar masses. If you have such a big black hole there, automatically you have material infalling, and in some cases, this can be really a lot of material that creates an accretion disk. So this one here, the accretion disk is, so to say, the mass that is really infalling into the black hole, and is giving the possibility to convert the mass here into the energy of the jet. Okay. This you have in 1% of the AGNs of the galaxies. Sorry, so that's why it's called AGN. 10% of the AGNs also have started to emit a jet of ultra-relativistic particle, which is an incredible guy, because it has a size. It's not that narrow. It's 1.01 parsec, but it can reach up to megaparsec length. So the acceleration it's really, really huge. Okay, so there is this jet. Now, the particle are ultra-relativistic here. So you can imagine that there is a lot of Doppler boosting. So if you look at the galaxy from this direction, it's like it is closer to you because of the space contraction, and you call it a blazer. But the galaxy, I mean, not all galaxies orient toward us. We are not so important. So if you move to a certain angle, you can call the galaxies, they have different features for you, and you can call them quasar if you're here, or radio galaxies if you are observing the galaxies from this direction. Okay. So the basic mechanism for the active galactic nuclei is infall of material. We saw the efficiency computation by Ghisellini, which translate into the formation of a jet of ultra-relativistic particle. This is a true image, and it's a beautiful image of such a jet. You see the dimension of these guys. It's millions of light years. Incredible. So from these jets, you have all the particles that you need. Okay, but now let's compare the magnetic field and the radius for the Euler's criterion. So in supernovae, these galactic sources, we said we had magnetic fields of the order of microgauss, radius of 1 parsec, and so we could get to 10 to the 16th of energy. But in AGNs, you can have stronger magnetic field, but especially you have a much larger radii for acceleration. Okay, you have more times if you want more space, and that's why you can get to 10 to the 21 electron volt as maximum energy. Okay, so really for those energy you have to go outside your galaxies. And how? Here we have the explanation of all these, the cosmic ray origin up to here. Okay, up to the very end. These are believed to be extragalactic. It's maybe there is a transition region here in which you can have very intense galactic emitter. This is something under debate, and we will get back to that. But now we know, okay, we may expect from energetic argument that these are from the galaxy outside, but also we have now a confirmation from Auger, as I was saying before. You may remember this plot. We have a spatial coincidence between the highest energy cosmic rays and the active galactic nuclei. Okay, so we have not only theory, but the experiment. Very recently, this is the mechanism, say. It's not, regardless the fact that we have observed many of them, it's not well known how this inflow of material, this is the black hole, can power a jet that lasts in that way. Okay, it's extremely important to look at really the lowest part of the jet, but unfortunately it's very far away. Okay, it's not very easy to see. So you may know about this ATH image. Okay, the image of a black hole, and it's probable now. It's probably clear that this is what is the black hole doing, is that is really twisting the magnetic field in this way, okay, simply by the charge rotation, and this is able to collimate the particle ejecta into the beam. Okay, I put here a link in which you can find many beautiful videos. Okay, this is actual data. And I just put here one because it's very nice to see from that page, but you can find many more. So M87 is in the Virgo galaxy cluster. And you see now there is a mixture between simulations and images. Okay, we have the galaxies, and now you will see the ultra-relativistic jet here. We have to wait a little bit to get to the central black hole. Okay, these are the inner parts of the jets until you finally see this, and this is the novelty. This is these lines here are due to the polarization of the light here due to the magnetic field there. Okay, so we know that we have this powerful engine, and it's a pretty interesting time now these years, because, so to say, simulations are now catching up with the true physics, which we didn't know before. So we are really close to understanding this mechanism, which was under debate for many decades now. Okay, I think I have tired you enough, but let me say a few more things. First of all, up to now, we saw this part of the spectrum, okay, in which we saw the synchrotron bump, the inverse Compton bump. But now we are able also to add the shy partner, the neutrino here, because we have seen actually with magic a coincident TV emission and neutrino emission from an active galactic nuclei. This is called TXS 0506. It has a method name, but from the same position we have seen not only photons but also neutrinos. Okay, and we are starting to really combine the two information. And you remember from the acceleration mechanisms how connected are the neutrinos to the presence of charged particles. So this is what is called multi-messenger astronomy, and it's a new field that is really underdeveloped. In order to also to predict neutrino is even more complicated, because you have now to really get into the exact particle physics that you have in the source in order to be able to predict the neutrino fluxes. Okay, but it's a new partner there. I want to tell you that the future will have many things to say. Okay, let me skip the gamma ray burst. The jets is very similar to what is the AGN, but it's really huge. The same energy of an AGN it's released in seconds. It's really a bright event that lasts only a few seconds in the sky. Okay, the power emitted is really amazing. Okay, so before the conclusion, but I don't want to stress you much more. I want to tell you about this gamma rays universe, that what you have to take into account for your dark matter studies, for me, is that you have not only a background, but you have a strong temporal variability. Okay, don't consider that the background is not only is what it is there, but it can change. You can have binaries, we said, you can have supernovae remnants, they can change in time. Please consider this as background in your studies. And if you're looking, for example, at the galaxy cluster, don't forget you can have many things happening there. Okay, the variability, okay, these are pictures of variability, but I don't want to tell you too much more. Just look here, the variability is incredible. This is a radio galaxy, GC 1275. No, this is IC 310, sorry, but it's there. That's the flux. And you see that in 10 minutes, you can change the flux by a factor of 5, okay? From a source that is millions of light years away from you, okay? So you can do what you want, but sometimes, of course, to have such a sudden change of flux, the acceleration sites must be very small. You cannot do it in 10 minutes, much more, no? And so you can have pretty interesting things happening there, and pretty much variability. You have it there, you have it in the binary systems, in which you have a flux, now more regular, but it's changing by 10, 20% along the time, okay? So the gamma ray flux is very variable. This is another target. Let me skip this slide. The spectrum is very changeable. Let me also skip this. So that's the first message. The gamma ray sky is varying. The second message is that I told you before, in order to understand our gamma ray sky, we need to know all the spectrum from the radio to the TV, okay? Because both these, they track the particle population. And that's why this is becoming an astronomical field. This is what we call the light curve. So this is time, and this is the flux. And we have to understand one source, not only in TV, so magic here, so low state, high state, flares, but in all the energy bands from TV to radio. And in some cases, as you see here, a flare in the TV, so a high state, is not reflected, for example, in radio, okay, or in TV or in X-ray, okay. So it's pretty complicated, the astronomy that is behind all this observation. Okay, let me skip these ones. Let me skip these ones too. The ABL, there will be a topic next Monday too, so I will also skip this one. So I'm going toward the conclusion for some take-home messages about all this. First, I found this cosmic ray thing really amazing. It entails a world of physics phenomena and information. There are galactic to extragalactic. Where are the main emitters? Is this only supernova remnant? Is there more? What is the role of AGNs? You have a lot of particles that contribute to this cosmic ray spectrum. Each one has his own story. We need magnetic field, but of course they can vary a lot, and you cannot study them that easily and to measure them that easily. So you have to make a lot of simulation and guesses. We have two main mechanisms: to have TeV gamma rays, the inverse Compton and the pion decay, which are able to tell us if we have electrons or protons there. Okay. And with this, we are able to build this nice gamma ray. So the connection between these two plots, the gamma ray plots, and this one is pretty strong. Okay. This is everywhere in the sky. This is from a specific target. I told you, we need to know a lot of astronomy to understand each gamma ray emitter. Pretty complicated. And you cannot know everything, so you need the humans have to really spend a lot of time understanding X, gamma emission, what is the particle mechanism, and so on and so forth. Okay, it's expanding field. Last comment before I close is that this field, it's really active. Okay, I quote here Haharonian, that is one of the leading experts in this field. In a recent talk, he said we had a complete revolution every 10 years so far. In the year 2000, our instrument, MAGIC and the others, they revolutionized the TeV sky. You remember my animation in which more and more targets were popping up, okay? That was 2000. In 2010, there was a revolution with Fermi and Agile of a little bit lower energies about the GeV sky. We learned so much. You are familiar with the instruments, I guess, about the GeV sky. We will take years to digest all the information. Oh, sorry, this is 2020. We have LASSO that told us that we have a peta-electron volt emitter in the galaxy, okay? That's also a fantastic new result. We are able to have acceleration that gives us PV photons in the sky, okay? So really, the revolution, you don't even realize that they are there because there are too many. More revolutions. We have the connection between gravitational wave and gamma in 2017. Between neutrino and gamma in 2018, the plot that I showed you before with MAGIC, okay? So there is a lot to say, and the things is not only theoretical, but it is related to the instrument that are able to tell us much more about this field. So this will be the topic of my Monday lecture, and I believe we are closer and closer to solving the cosmic ray puzzle. Okay, so this will not be done by these three guys. But I hope that out of the confusion of and maybe geocentric model, we will be able to see everything clearly, like it was done a few centuries ago for the motion of the planets. Okay, so I hope I didn't talk too much. I know that I didn't take a breath. I hope your brain is not fused too much, but I want to thank you for listening so far. And I'm here for a few minutes of questions if you have.
Thanks a lot, Michele. Some questions?
Gabi.
So I had a question. In particular, why is the accretion disk and the relativistic jets perpendicular to each other? Like, does that have to do with the spin of the black hole and something?
Exactly.
So why is the accretion like in a particular plane? As
So the accretion is in a plane because of friction of the standard friction that you have, like the galaxy is on a plane. No, you have friction, and you create a disk of infolding material. On top of that, you have the rotation of the black hole, but is not necessarily for the jet. So this accretion of material goes into a plane, and then this is not only neutral particle, there is an excess of charged particles that allows you to create this magnetic field that takes the direction perpendicular to that very plane.
Okay, thank you.
More questions? Well, we have other ones in the chat. For example, Claudio Muena say, how about star formation zone? Maybe if you want, Claudio, say what is the slide that you are referring?
I'm also seeing the chat. Good morning.
More questions.
Star formation zone. I'm not an expert of star formation zone because I think the signal there in star forming region is more on the GeV side. Okay, GeV is observed with satellites such as Fermi, and while I'm more expert of TeV radiation. So, but the idea is always the same. When you have star formation, it means that you have a dense region and you have a lot of ejecta from the stars. And when you have ejecta, you have ejecta with kinetic energies, and then you have winds. And when you have winds, you can sustain this acceleration. Okay. But the details there of the maximum energy, I'm not familiar. But this is, anyhow, the idea is pretty similar to the rest. Does the flux in figures include all kinds of cosmic rays or only photons? I don't know which figures, Yun, you were referring to. So cosmic rays is a term, the cosmic ray spectrum is particle spectrum. Okay, so maybe that's the answer. So just particles. Was it all that clear?
More questions? No? Comments?
I have a quick question, if you can hear me.
Yeah.
Can you hear me?
Yeah.
Yeah, okay, good. I was a bit... No, I was wondering a bit about the extragalactic background light. Yeah. I don't think that you talked a lot about it.
No.
Unless I somehow managed to miss it. But could you maybe explain what it is and what role it plays?
Maybe I think there is there a talk about this, Miguel Angel, next week? But anyhow.
Yes, exactly. On Friday, this Friday morning.
Exactly. That's why that's why I didn't spend that much time. But the idea is pretty simple. So you have when you have you have photons from stars, okay, in the infrared or ultraviolet, okay, really photons directly emitted from the stars. These, as you can imagine, they permeate the universe. They can be. I have actually a picture. I can show it there. They permeate the universe. They can be upscattered by dust grain. Oh, here. Okay. So this is wavelengths and this is flux. You see that you can have this bump here. These are lights from, say, zodiacal lights, but also from the stars here. Okay. Now these low energy photons, if you make the numbers, they have the right, especially those in the infrared part, they have the right cross-section to TeV photons for pair production. Okay, so you see this, the plot here on the top. You have the gamma ray photon from, for example, from the AGNs, and you have infrared photons from the EBL, and you lose them by pair production. This tells you that, I mean, there is a certain distance above which you cannot see. This is the plot that tells you about the distance. So this is the energy of the gamma ray photons, and this is the optical depth. So the optical depth of a 10 TeV photon, for example, is, okay, depending on the redshift of the source, is 0.03, 0.01, 0.03 according to different model. Okay, but anyhow, you cannot go say that much farther than 0.5 as redshift. Okay, so optical depth. I got muted. Okay, so it's very hard to see photons above 10 TeV from sources farther than 1 TeV. Okay, because of these mechanisms. That's why you are blinded. So the 100 TeV photon, they must come from very close to you. So you cannot probe the cosmic rays through the gamma rays outside our galaxies. Okay.
Yeah, so this sounds very similar to what you said in the beginning.
Exactly.
But then you talked about scattering or pair production on CMB photons, if I remember correctly. Yeah. Okay.
Yeah. Sorry.
Is there anything particularly different about this?
No. I think I made a mistake at the beginning. So you can do also. You have this interaction with the cosmic ray background, which is here. Okay. Which is much more intense. You also have, but this effect, a different kind of, a little bit higher energies. So maybe this part here. So I should modify my early slides for both CMB and EBL photons. Thank you for noticing that.
Does that mean that the sky is more, or that space is more opaque than what you said, or?
Yeah, that's with the EBL photons. Okay. Mm-hmm. With the CMB, it just simply, the CMB, it is what it is, and this is a, so to say, a maximum limit, but it's larger than that. This shape here, the opacity of the universe in gamma rays is due to the EBL interaction, and we thought that now it's more transparent because by this plot we didn't expect to have targets above 1 in redshift, but we have found one. Okay. And so this means that in a certain sense it's less opaque. This means that the EBL, the intensity of the EBL is say smaller, lower than expected.
Okay, well, let's break here just to stop for a coffee or something, coffee break. If you want, Miguel will be in other town later for more questions, and also the people that want to stay in other town now is open. So see you in half an hour or less, okay? See you after coffee break. Thanks a lot, Miguel.
Thank you.
Bye.